So, now we will look at the extinction of peaks for some interplanar spacings. In this case, we will take a BCC unit cell. Consider a simple BCC unit cell with a cell parameter A naught equal to 3 angstrom. Let X-rays with wavelength lambda, which is equal to 1.5 angstrom, be incident on the 1 0 0 phase. So, now we will calculate the structure factor. So, this is the structure factor equation because of the 2 atoms per unit cell. So, when HKL are all even, such as for 2 0 0 planes, for example, the terms for the corner atoms, that is e power 0, and the body centered atom e power pi I into h plus k plus L atoms are plus 1. That means, what does that mean? That means all atoms scatter in phase. And a 2 0 0 peak is present. So, according to this rule, all atom scatters in phase. So, these things you have to remember, and 2 0 0 peak is also present. However, when h plus k plus L are all odd, such as (1 0 0) planes, the terms are plus 1 and minus 1 respectively. and the two sides exactly out of phase. And there is no 100 peak. So, in fact, what I have written is what I have shown in the slide, in the previous slide where I showed the reciprocal lattice, where you could see only these kind of planes, not this kind of plane, because of this extinction rules. Now, we can prove this concept geometrically. We first solve Bragg's law for scattering from Bragg's law. We can write for scattering one planes, lambda is equal to 2d (1, 0, 0). Let us understand what I have done so far. From the Bragg law for scattering from 100 planes, you can simply write lambda is equal to 2d 100 plane sin theta 100, from which we can find out the sin theta value. Sin theta is equal to 1.5 divided by 2 into 3, which is equal to 0.25, correspond to the theta 14.48. The difference in the path length between rays 1 and 2 of the rays shown in the slide, you can see that we can obtain it from sin theta 100 equal to AC divided by D100, which is equal to BC divided by D100, which is equal to 1.5 angstrom, which is 1 X-ray wavelength. So, that is what we have started with. So, it is 1 X-ray wavelength. Now, the question is, what is what about the X-rays scattering from 200 planes at the angle theta 100? So, we can find out in a similar way. The path length So, the path length for 200 planes is 2 times A dash C dash, which is equal to 2D sin theta 100. If you can substitute this, you will get 0.75 angstrom as a path length, which is half of the So, what is the consequence if you have the path length from 200 planes is exactly half the wavelength as we have discussed previously? It will completely cancel out the intensity. We can write that, which will So, when you have the path length for 200 planes is as half a wavelength, then the waves from these planes completely cancel with those from 100 planes. That is why you do not see the peaks like 100, 300 and so on in that reciprocal lattice. Now, let us consider the scattering from So, let us consider the scattering from 200 planes at the angle theta 200. If you look at the slide, the figure B shows this schematic, excuse me, and then we will now proceed with the calculations. And the Bragg law for this case gives sin theta 200 is equal to lambda by 2d 200, which is nothing but 1.5 angstrom divided by 2 times 1.5 angstrom, which is worked out to theta 200 is 30 degree. Now, at this angle, the total path difference the total path difference is 2 times AC, which is 2d 00 sin theta 200, which is nothing but 1.5 angstrom, which is nothing but one wavelength. Now, similar question what we have asked there, what about scattering from similar question here, what about the scattering from 100 planes at the angle of theta 200 now? Then we can work it out this also. The total path difference So, the total path difference in the case of scattering from 1 0 0 plane at the angle of theta 2 0 0 is 2 times a prime c prime, which is equal to 2 d 1 0 0 sin theta 2 0 0, which is equal to 2 into 3 into 0.5, which is nothing but 3. 3 is 2 lambda. This value is nothing but 2 lambda. This is which is nothing but an integral multiple of wavelength lambda and supports the constructive interference process. So, from this example we have seen how this the 2 0 0 type of planes exist, and what is the meaning of extinction of certain peaks in for some interplanar spacing in crystal, in a cubic crystal like a BCC. So, these two examples gave you some kind of an appreciation for this concept, and now we will move on to the next example what I would like to show. Come back to this slides. If you look at this slide, this is a structure factor calculation for a face centered cubic structure, and if you write the expression, you have 4 atoms per unit cell. So, you get the 4 terms here. So, 1 plus e pi I h plus k plus e pi I e to the power pi I h plus L plus e to the power pi I into k plus L. So, the rule is f h k L is equal to 4 f, where h k L all even or odd, and the intensity will become, our structure factor will become 0 when h k L are mixed. So, now you can see that this is again a reciprocal lattice cell. So, do not confuse this with your real cell. This is a reciprocal unit cell. That means you will see the intensity spot actually in a double cell size, and wherever you have the allowed reflection, then only you will see the dark circles. So, here you can see that all HKL all even or all odd will have the allowed reflections. So, other positions are forbidden. So, what you can now appreciate is the reciprocal unit cell for an FCC lattice actually a BCC lattice, and it is the same thing what we have seen before. It is the other way around. For a real BCC lattice, the reciprocal lattice is an FCC unit cell. So, that is clearly appreciated here. Now, we will see some interesting examples. A cesium chloride structure where you have a cesium chloride type of structure, you can see that it is kind of body centered unit cell, has got 2 atoms, that is chlorine and cesium atoms per unit cell, which is one in corner, another is in the body centered position. But you can write the expression in terms of the structure factor equations like this, and the selection rule is, you see FHKL is equal to FCL plus FCS, where H plus K plus L is equal to 2n, and if it is FCL minus FCS, where H plus K plus L is equal to 2n plus 1. see what you have to appreciate in this particular example is, though it is a BCC crystal, it is since it is chlorine and cesium are two different atoms, it is to be considered as two BCC crystals are interpenetrating with each other. It is a kind of an ordered system, and you should also appreciate that since these two atoms are very different, chlorine and cesium, their scattering factor will be very different as an individual atom. So you will see instead of in some reflections, instead of a sum of the peak intensities, you will see the difference in that scattering power. That is why you see in some terms it is plus and some term it is minus here, and the corresponding effect you will see in a bigger circle here, that means higher intensity, that is sum of intensity, and then you have some of this, it is the difference peak. This is a difference peak, this is a sum peak, that is what it is written. The peaks for which H plus K plus L is even are sum peaks. That means when H plus K plus L is equal to 2n means a sum peaks and are bigger than those with H plus K plus L is odd, something like the red spot here, which are all difference peak. It is not a sum peaks, it is called a difference peak here, and this is again a reciprocal lattice cell, and you will be able to appreciate this when you look at the electron diffraction pattern much more clearly. You will see this kind of an evidence, actual practical evidence for the difference in the intensities, and this structure factor calculation nicely shows that the difference in the intensity is because of the factors like this. Now we will move on to another important crystal system called a sodium chloride structure, and this is similar to cesium chloride. You have two interpenetrating FCC crystal units, and you can see that the two positions are mentioned here. One and this is a final expression what we have written, and you can see that FHKL is equal to 4 times FCl plus FNA, where HKL are all even. That is a sum peak you will see, and there is a difference peak when HKL are all odd, and if they are mixed, there is the structure factor is 0. So you can see this, you can look at this selection rule and then corresponding the reciprocal lattice structure. You can see that a sum peak will have a higher intensity, that is larger circle, dark circle, and then there is a difference peak like 1 1 1, you will have a lesser intensity, and then you have a 0 intensity in HKL are all mixed like this. So it is just to give you an idea how the structure factor nicely gives you the idea of the intensity summing up, or it is becoming 0, or it becoming the difference in the scattering power of the atoms. So these illustrations clearly shows simply demonstrate the significance of the structure factor in appreciating the X-ray diffraction intensity. So having said that, we are only interested in appreciating or understanding the intensity from a single crystal, or it could be a polycrystal, or it could be an amorphous material, but we have to now look at the intensity expressions, what are all the term it contains. So before we really get into that, we have to appreciate what are all the factors which influence the intensity, that we have to look at it. So before I get into that discussion, let me tell you we have when you look at the X-ray diffraction spectrum, in every peak there are two things. You have I max and you have the breadth of the peak, or the integrated intensity. There are these three things are very important. I max is always not important, but it is the integrated intensity which is important, which is the area under the whole peak, and this is influenced by so many factors, and this we have to understand one by one, and then how this, the broadening of this intensity, X-ray intensity peak, is related to what we are looking at in the material. That is also another important factor. We will look at one by one. So, I will go back to the blackboard again. So, before we talk about the intensity of the X-ray peak, we should know what is the theory behind it in when it being calculations are carried out, and so you see that the kinematical theory is used for calculating the intensity of X-ray, and it has got some assumption which is very important. So, I will write down three important assumptions. So, the kinetic theory of diffraction assumes these 3 points, that is, no interaction occurs between incident and the scattered waves. Secondly, waves are scattered only once, and thirdly, scattered waves do not lose energy. So, based on these assumptions, the intensity of the X-ray is being calculated. And then now I will just list out some of the factors which will influence the X-ray intensity. There are 6 factors. So, there are 6 factors that will affect the relative intensity of the diffraction lines in a polycrystalline material. One is a polarization factor, which we have already seen it. You know, you have some idea about what is polarization factor, and then structure factor, which we have now seen. So, at least these two are familiar. The third one is multiplicity factor, and fourth one is Lorentz factor, fifth one is absorption factor, and sixth one is temperature factor. So, all these factors have to be taken into account when you write a complete intensity expression for a diffracted beam. And before we get into all this, you have to remember that of course, this intensity also what you obtained is depending upon the method by which you perform these experiments. There are primarily 3 methods that also I will write before we get into the intensity discussion. So, there are 3 methods. One is Lave method, another is a rotating crystal method, and third is a powder method. I will not get into the theory of all these things. I will take you to the laboratory and then actually show what are the typical methods we follow in the X-ray diffraction laboratory when we actually perform the experiment. Just for the sake of completion, you should know the basic method of conducting this diffraction experiments. When in a Lave condition or a Lave method where the lambda is variable and your theta is fixed. In a rotating crystal method, lambda is fixed and your theta is variable partly. And in a powder method, you have a fixed lambda and then variable theta. These are all just about the methods by which you measure the X-ray diffraction intensity for a polycrystalline material. So, we will look at the importance of the variable lambda and fixed theta or fixed lambda and variable theta when we do the laboratory demonstration. So, now we will come back to the intensity of these X-rays. You have to have some idea about what all these factors mean. We will not get into the very detailed of the calculation of this or derivation of this, which is out of the scope of this course, but you should have some idea what is this factor, because all these factors are going to come in the final intensity equation, and then we will briefly go through what is this multiplicity factor and Lorentz factor and absorption factor and temperature factor, so on in the next class. Thank you.